Okay. Okay. Well, I think you may have noticed that this is the first conference. First of all, well, before I begin, let me thank James Waters in particular. He's not here, but I hope he watches the rebroadcast of this symposium. Thank him for supporting this really quite remarkable set of symposia. It's the first of the 22 others that takes the laboratory equipment and brings it to the point of use. And that's increasing, that trend is increasing, and I think there'll be more such symposia. So let me begin. Niton. Well, Niton comes from the terry, to shine, from the Greek. It's another name for radon. Its symbol was NT. It's obsolete as of 1922. But my wife, who's a crossword puzzle maven, gave us the name. I had started a student-run project at MIT to test the homes of the MIT community for radon. And it was a liquid scintillation counting technique. I found that old scintillation counter when I was walking through the chemistry building. They were throwing it out. I took it to my lab, started this project. We did about 2,600 homes, wrote a report. Project ended. My telephone kept on ringing, and in a fit of whatever, I founded Niton in 1987 to commercialize the radon testing by absorbing the radon in charcoal and measuring the amount of radon from the emissions into liquid scintillation. The first president was my son Hal, who is here. He began, I believe, I haven't checked with him, but I believe there were 2 more employees. Business was not brisk, and he left for San Francisco in August of 1988. And my sister, Ethel Grodzins Romm, comes to take over. We're a bootstrap company, and in bootstrap companies, I can tell you that necessity trumps nepotism. Well, she had wide-ranging experience. None of it was technical, but she is an accomplished problem solver and a successful New York City executive. And she came on Monday, September the 12th, 2088. 2008. I thought I'd corrected that 3 times. So 1988. I hope I have the right set of slides here. Well, the next day, the very next day, these are the headlines in the New York Times and the Boston Globe. Radon is a serious problem in the homes of the people in the United States, and in particular in Massachusetts. Where is the little pointer? And that goes on. Oh, here it is. So here's Massachusetts for those who come from abroad. Anyway, the Boston Globe has a similar headline which says 60 or 70 people per year expect to die of radon. And as my sister Ethel says, we were extremely fortunate because this was a very slow news day, and this was the only news fit to print. So here is Ethel, and even with all of the qualities that she had, it is better to be lucky, right? The business was successful. It really grew very rapidly at that particular point, but it was definitely low tech. And so I'd been playing with ideas for a monitor, a real-time monitor of radon, and I thought that I had invented a wonderful technique. It wasn't being used by anybody of the various radon detectors that were out in the market. This particular method seemed to be absent, so I started to apply a patent when I realized that it was very well known, probably by Madame Curie. I mean, it was a very old technique, but two people, Stephen Shevsky and Charles Parsons, modernized it with modern techniques, and we had a business in the active continuous monitoring. Well, here is Steve Shevsky. He was a 38 student at MIT, did his senior thesis with me, decided not to go to graduate school, and of course I grabbed him and said, how about coming to Niton? And he did, and he's still at the company. Charles Parsons, he died tragically in a parachute accident in 2001, but he was the polymath of my large high-energy nuclear physics group at MIT. It was large, about 20 people, lots of students, and he was the go-to guy, could do everything. He consulted for Niton while a graduate student, and he joined us after his PhD in 1992. And here it is. This is the Niton Rad 7. I'll come back to that. Here's a picture of Steve Shevsky. As Steve and Chuck made the Rad 7 more accurate, more versatile than it had to be. That's the theme of this talk, in fact. They didn't have to make it this good. They did. As a consequence, it is still being sold. There are some 100 to 200 of these sold every year. It has a different name. It has the name Dubridge, if you could look at that. But it looks exactly the same. Its qualities are such that, as we knew, it could measure radon and it could measure thoron, which is a different isotope of the element 86, which is called the element's called radon, but we think of radon only in terms of radon 222, which is the one that's the dangerous one. But that spectrum, which is the kind of spectrum that you get, is laboratory grade. And as a consequence, this instrument is used throughout the world for radon testing, for water quality testing and water research using radon and thorium. Well, we were now part of the community of home inspectors and the EPA and that group, and they sent out a request for proposals. In 1991, the EPA funded 2 SBIR awards to develop it. And they both won second and third phases, both made successful commercial products. In fact, we and RMD divided the market for lead paint inspection. The RMD's K-shell analyzer was by far the best K-shell analyzer around, and everyone else's besides us was a K-shell, but they couldn't develop it any further, being a K-shell analyzer. It was an instrument which said there was lead that complied, there was lead that didn't comply, and that was it. Niton's L-shell analyzer, that led quite directly to this symposium. Well, let's go through the L-shell method to tell you how that happened to come about. Well, the L X-rays are at 10.5 and 12.6 keV. They're easily absorbed, and therefore it was believed that out-of-compliance lead, that's lead more than 1 milligram per square centimeter, buried between layers of lead-free paint, cannot be distinguished from compliant lead near the surface. Mathematically, there are only two measurements, the L alpha, the L beta, and there are three unknowns. The lead concentration, the thickness of the covering layers, and lead had been banned for paint for some years by this time, and the chemistry of the covering layers, and how can you solve for the lead concentration. But the fact is that a calibrated detector, calibrated on a known amount of lead, like 1 milligram per square centimeter provided by NIST, allows you to do this with only two unknowns: the lead concentration in milligrams per square centimeter and the relative absorption of the L alpha and L beta X-rays. Measure the ratio of the intensities and the absolute intensities of one of them, determine the absolute concentration of lead. I obtained several patents on this idea, and I should mention that it rests on the fact that the Compton scattering is negligible for low-energy X-rays. That's what you have to put into the mathematics to make this thing work. Well, you've got to measure the absolute intensity and the relative intensity of two peaks. Well, we introduced the silicon PIN-Diode as a detector of those. The initial resolution was about 900 eV. Let me pause a moment just to say that one of the gifts that comes free with being a professor at MIT is that you're really connected with a very wide community of forefront research. And there I was in high-energy research. I had dabbled in synchrotron radiation. I was very conversant with the X-ray astronomy group at MIT, very familiar with what's going on in CERN and other laboratories. And we knew that the PIN-Diode was used for measuring particles. Why not, when you looked at the numbers, why not use it for this? We tried it, it worked. And I'm now going to show this next slide several times. This shows the detector resolution that we and AMPTEK obtained in 1991 and the improvements that AMPTEK, Reed, Alan Hoover, made over the next decade. Alan will be giving a talk a bit later. Those improvements are a central reason why we have this conference today. The central reason why laboratory XRF is being replaced in large part by handheld XRF. Well, this is really Alan's results smoothed and added to. That is, here is the year from 1990 all the way to 2010. Here's the full width, half maximum in electron volts. I believe he's going to show you what he obtains for the noise. I simply convoluted the statistical Fano factors into it to get this curve. We were in that era, we're in region A. That's noise dominated. All peaks have the same full width and half maximum. Terrible. 900, you can't use that for looking at multi-elements. You can't use that for EDXRF. But you can use it for this problem, for the lead paint problem. Here are the two peaks. There's 10.5 to 12.6, 2,200 EV. 1,900 EV resolution gives you peaks of this kind. You can measure the ratio, you can measure the absolute intensity, you can measure the lead concentration beneath layers of paint which do not have lead in it. And so we had a lead paint instrument Charles Parson led the development. He insisted that we start using the latest technology being used in physics, namely digital processing throughout. I think we were digitizing at 25 megahertz, but I have nothing but my memory, which is pretty lousy, I should tell you, to go on. The full energy spectrum was displayed, which was of no interest to a lead inspector. Oh my goodness, what is that? We buried it. Okay. The DSP, the digital signal processing, was much more powerful than it had to be. And here is a picture of Chuck. And here is the prototype. That's what it looked like. You can see, and just to show you that it is real, here it is. A 1.5 pound instrument you can carry in your pocket, which I've been doing all day. There's no radioactive element in it. But the shutter is closed. And when it was really had a better resolution, it won the R&D 100 award, where he put in a multi-source instrument so that there were not only monochromatic X-rays coming out at 22 kilovolts, but we also had an IM55, 5.8 kilovolt. We had, and we had we had up to 3 sources in there. And by the 1994, our resolution of 350 eV gave us these kinds of results for lead, much better than before. Good enough because the gap between the K energy of, say, iron and the K energy of cobalt, the next one over, is 500 eV. We have 350 eV. Good enough for not so very sensitive measurements. And so now we're in the alloy sorting business, and you see where we are. I've given you now the width for the 5.9 keV line of manganese. Here it is, as a function of Allen's results. And I've also given what you would get for the K line of silicon at 1.7 MeV. That's for the future. Well, Ethel transitions to Hal. Ethel was president from 1998 to 1996. Superb leader, resourceful, always optimistic, grew the company through good and not so good times. Hal joined in leaving behind a highly successful brokerage position in New York City. He spent months analyzing the markets. He became convinced that a handheld XRF instrument had huge potentials in the broad metal alloy community. And there's a picture of Hal. Who's here tonight? Well, what were his goals? I have to tell you that when I say those were his goals, he never stopped pushing me about getting those, of reaching those goals. And I just assumed that he never stopped pushing anybody else. One of them was the brick had to go. What kind of ergonomics is this? It has to be a gun type. It has to be a gun type. Radioactive sources. He did analysis. Will grow, but there's a limit. We can't get beyond this number because radioactive sources require licensing, you will name it, disposal, all the various things. That's going to limit our growth. We must develop a handheld system using an X-ray tube, and I was going all around the country trying to find people who could make an X-ray tube. And he was going with me and going separately. The energy resolution is central to our growth. We must work with AMPTEK. Allen is pushing the envelope, and we have to be part of that. We have to work with him. The speed of testing is critical. We must have the fastest signal processing. That was at Jordan and analysis. Steve Shakespeare. The SDS is the future, but we knew about it. We must be first. You know, the SDS, the silicon drift detector, invented by Gatto and Renko back in the 80s, was known to me for high-energy physics, as position-sensitive detectors. I knew that the astrophysics community was going full tilt, making very large SDS instruments, detectors, 4-inch diameter, 5-inch diameter. Can we use those for, and people were already testing them for the research community for X-rays. Could they make them commercially? And we started way back. Well, here is a picture. I don't know what date that is, but it's clearly with Ethel and Hal there. It must be in the 1997 region. 1996. 98? Thank you, Hal. Well, there's a picture with Ethel, there's Hal, there's Steve, there's Chuck. Well, there's one of our speakers is coming up, and I think you might recognize some of the others. Jim Pasmore is up there. He's here at the conference. Well, there's our pistol grip, but there are many others. Hal was pushing us to make new and better systems. Well, what were the applications? Many, it turns out. First, there's lead. Well, there's the lead in the walls, but there's also site assessments and other things. There's the metal alloys. There's the recycling. There's fabrication. There's the mining, exploration. There's the trace elements. There's the environmental. There's the archaeometry. Let's go through a few of these. Here's the metal alloys testing market. I just want to show you that some of these instruments were taking 1,000 measurements a day or more. Here is the positive identification of the actual alloy being measured in situ. Here is the mineral exploration and mining. Let me pause and talk about this for just a moment. This is the environmental market, and here you see them taking measurements of the lead, the arsenic in soil. Up until this time, the way people did this was to take samples from a large area and then go and take milligrams of it to get very high precision and accuracy on the milligram quantities, but terrible results for the average value over the large acres of ground. Here, you could take measurements, 1,000 measurements in a day. With GPS, you'd know exactly where you were with each measurement. You had you not only got the results in the same day, but you got a much better set of results when you were finished. So, the advantages, results in less time, minutes, not days, no restrictions on the number of tests. How much time do I have?
You have about 6 minutes left.
Okay, yeah. No restrictions on the number of tests. Point of use gives immediate results. The procedures can be changed on the fly. Oversampling adds negligible cost. Mistakes can be caught and immediately corrected. I haven't listed them all, but the cost per test or the cost per job is dramatically reduced, and the instrument usually pays for itself very quickly. People in the recycling metals market, in the junkyards, would take these instruments, find that some material there's tons of material which might be worth 10 cents a pound more because they knew exactly what the elements were in. And they made back the cost of their instrument in one day. On-site analysis becomes practical. Positive material identification in existing equipment. Eco-cleanliness of manufactured goods. Mining applications in the mine walls themselves becomes practical. Scrap metal analysis can be done at the junkyard and the bidding site. And driving that growth was the incremental improvement in the portable instruments, opening up new applications and finding markets within the laboratory equipment market. And so now we're at the silicon drift era, which I'm not going to speak about, except to say that we're now at the point where a room temperature device, cooled very to modest temperatures by Peltier-cooled, have resolutions which rival those of liquid nitrogen facility detectors, have count rates of 10 to the 5th and higher, and that's throughput count rates. I was getting 150,000 when the test that I did with these kinds of. Well, what were the innovations? There were lots, and I'm not going to detail them. The one-piece handheld, we won an R&D award for the 309, the multi-element analysis, the multi source systems, the mining system, the 35 keV X-ray system, first with the AMPTEK Marlbrook, and Charles will be speaking about those. Whoops. And Newton Scientific, Bob Klinkenstein, who supplied most of our X-ray tubes. The Infiniton, I love that name. I don't know who made it up, but the Infinity Niton, using an americium source which lives hundreds of years, non-replaceable. You can use it forever to do XRF. We won the second R&D award with a whole host of them, including the first X-ray tube, helium purge and 50 keV, and then we won the third. Handheld energy dispersive XRF have attained the capabilities of all but the upper end of laboratory instruments. Workers in numerous industries make rapid and accurate sensor measurements. With each gain, the handheld XRF opens up new markets, encroaches further into the domains of laboratory instruments, and I believe that the handheld instruments have the potential to continue their growth. Thank you very much.